All right, awesome. So we've got the recording started for those people who may not be able to make it in person today. So welcome to EDPD 5456. So this class is all about algebraic reasoning. And the goal of this class is to help you guys improve your pedagogy or like your teaching skills for algebraic reasoning topics, as well as to expand your content knowledge. So some of your assignments will be more teaching oriented, and other ones will be more helping you understand the content. So before we get started with the syllabus and all of that information, I want to do a little activity with you guys. So if you can grab a piece of paper or something to draw on really quick, I'm going to have you draw two pictures. Okay, so the first picture is going to be a picture of a pig, and the second picture is a picture of the number 3. So they don't have to be like super nice, just quickly sketch out a picture of a pig and a picture of the number 3. And once you've got that done, just type done or something like that in the chat so I know that you're finished. Mhm. Awesome. Thanks, Castina. Sherry, Anita, Jeannie, awesome. Kylie, thanks. Me, Shelly. So, okay, now I'm going to show two pictures on the screen, and I want you guys to identify which one your picture looks the most like. So when you look at your first picture, does your picture look the most like the left-hand side or the right-hand side? And just again, type it in the chat, either left or right. Okay, pretty much everybody has said the one on the right, which makes sense, right? Because I told you to draw a picture of a pig. I didn't ask you to spell the word pig. I asked you to draw a picture. So now I want you to look at your second picture and share in the chat. Does your picture look more like the left or more like the right? Okay, awesome. So the reason I wanted to do this activity is because I've done this activity with hundreds of students. I like doing this with my undergrad students as well. And almost always, people will always draw a picture of the number 3 as the numeral 3. So the number 3 is not the symbol that we use to represent it. The number 3 is the idea of having 3 things. So the number is actually an idea or a concept, and the symbol that we use to represent it is technically called a numeral. Now, I don't necessarily expect you guys to get into the pedantics with that with your students, but it is important to understand because math is a language, and the symbols that we use in math are just like the symbols that we use in English, or really any language, to communicate ideas. But it's really important that we don't only focus on the notation so much without giving our students a connection to what the idea is that it means. And this is one reason why it's so helpful to use manipulatives when you're teaching concepts to kids, because it will give them a conceptual understanding of the idea behind it. And then you can teach them the numerals and the symbols to represent those ideas. Does that kind of make sense? The difference between um, the concepts behind what we teach our students versus the notation that we use to denote it? Okay, awesome. And as kind of a little tangent, I believe that this is one reason why people often struggle with math. As a middle school and high school teacher, and now a college teacher, I see a lot of students that struggle with math. And the number one thing that I can trace it back to is that they don't have a conceptual understanding of the concepts. They've just memorized how to manipulate symbols. And for some students, this can start relatively early when they memorize math facts without really understanding what the math facts mean. Um, and so one of my main focuses in this
Talk with his
class,
own lineman.
oh, let me mute Tyler real quick. Here we go. So one of my main focuses in this class is to help you guys learn how to make the connections between patterns and notation yourselves, but also to learn how to help make that connection for your students. So one of the common themes that will show up in this class a lot is the theme of making conjectures. So basically helping your students look at patterns and find patterns and then describe those patterns and prove why those patterns will always be true. Also, if you guys do have a question or anything, feel free to click like the raise hand button, or if you can't find that, you can also type like question or hand or something like that in the chat, so I can call on you. Okay, so that's kind of my overall goal for the course. And now I'd like to just quickly go through the syllabus and show you guys kind of how the course is going to work and what types of assignments we'll be doing in this course. So let me pull this up. Okay. So to get to the syllabus, hopefully you guys have used Canvas before. But if not, this is the homepage. You can get to the syllabus from here, and the modules from here. So the modules is where all of your assignments are listed. Or you can also access them on the left. So we'll go to the syllabus. This class is entirely online and asynchronous. So this meeting that we're having right now is the only in-person or on Zoom meeting that we'll have. Excuse me. But I am happy to meet with you guys for office hours, or if you need to jump on a phone call real quick, I'm happy to do that. In previous semesters, I did have a specific time for office hours, but not very many, like I think I only had like one or two people come. And then other people needed to meet at a different time. So because of that, I'm just doing my office hours by appointment this semester. So if you want to meet with me or have a quick phone call with me, just send me an email and we can schedule a time to meet and discuss whatever you would like to talk about. Also, just so that you know what you need to plan in terms of your time commitment, this course may take between 10 to 15 hours of work per week. So a 3-credit class at the college level should take between about 90 to 100 and I think it's like 140 hours total. This class doesn't take quite that much time, but you should plan on about 10 to 15 hours of work per week. And if that's something that doesn't really feel feasible right now, I believe they will be offering this course again in the summertime, if that works better for your schedule. So that's office hours. My response time and feedback. So I respond to my email about once per business day, and usually it's in the morning. So if you send me an email in the afternoon, and you don't get a response that evening, don't worry, that's normal. But I will respond to you the next morning when I get back in the office. Um, and then my goal is to provide grades and feedback for you guys within 1 week of the due date. And I'm going to prioritize grading assignments that are turned in on time. So I do accept late work and I don't take off late points. But you will get feedback faster if you turn in your work on time. So that's some information about my response time. We do have a textbook. It's called Thinking Mathematically by Carpenter, Frank, and Levi. So if you haven't already ordered that book, make sure you do that soon. You should be able to finish the assignments even without the textbook. because this is a, like, supplementary reading to help you, um, like, think about the ways that you can integrate, algebra into your elementary classes. But you should still be able to work on the assignments even if your book is a little bit late coming. I also will have additional videos and reading materials that will be posted in Canvas, but this is the only textbook that you need to purchase. I'll let you guys read through the course outcomes on your own, but I want to focus on our four assignment categories. So we have four assignment categories, and the main ones are the case studies, conjecture projects, and the final exam. The homework is worth 10%. And this one is basically just completion based. So you should get full points for it as long as you complete it. And the homework assignments will help prepare you for the final exam. So we have 7 weeks of class, and you'll have a homework assignment, a case study assignment, and a conjecture project every week for the first 6 weeks. And then in the last week, that will be when we have our final exam. So, and this is the way that the weights are split up. So the final exam is 30% of the grade. The conjecture projects are also 30, case studies are 30%, and the homework is 10%. And kind of the goal of each type of assignment is the case studies are going to give you examples of how you could implement the ideas of algebraic reasoning in your classrooms, and how to help your students build conceptual knowledge versus just memorizing processes. So the case studies are very pedagogy focused. The conjecture projects are ones where you guys will be making your own conjectures and proving those conjectures. Because again, one of the main goals of this class is to learn the process of forming conjectures and proving conjectures so that you can help your students form their own conjectures and also prove those conjectures. So I'll spend a little bit more time talking about those so you guys get a better idea of what that will look like. But the conjecture projects are more content based because it's going to be you guys practicing observing patterns and using algebraic notation to describe those patterns. And then the homework and the final exam are just going to give you some basic content knowledge. So like in this first week, you're going to be learning about different types of numbers and how they're related and how they build on each other. In week 2, you're going to learn about integers, and they're just more general concepts. And I'll also have videos that explain how to use models to help the students build a conceptual understanding of those concepts. Do you guys have any questions so far? You can either come on mic or put it in the chat if you do. Okay, awesome. Then let me go through a couple of example assignments so you can see what this looks like. So I'll go to modules. And they're all split up into weeks. So the overview gives a general overview of the week and what you'll be learning. In the readings and videos assignment, this one will have a list of the chapters that I want you to read. So like this week, you'll be reading chapter 1 in our textbook. And then I also have a couple videos that cover the concepts for that week. So these videos will typically be correlated to the homework and eventually the final exam. So if you ever like need to cut out an assignment and like do it later, the one that I would recommend doing would be the homework, because ultimately the homework won't be assessed until the final exam. So if you ever need to skip an assignment because you've got like a super busy week, I would recommend skipping the homework. And if you need to, you could also skip these videos and then go back and do them later when you have more time. The ones that it's important to do when they're due is the case studies and the conjecture projects. The case studies are important to do on time because your discussion posts will impact other people's ability to complete the assignment. And the conjecture projects are important to submit on time so that you get my feedback in a timely manner, and can resubmit them, if you need to resubmit them for a higher score. So for the case studies, it's set up as a discussion board, and you'll have, usually it's about 10 case studies that you'll be reading. And the PDFs are provided in the assignment, and all of you are assigned a specific case study. So you'll be reading all 10 of them, but you'll only be writing an in-depth analysis for the one that you're assigned. And if you're not seeing your name on this list, you might be in the other section. But basically, for the assignment, you're going to write a 3-paragraph analysis of whatever case study you were assigned that addresses these 3 questions. So you'll notice what conceptions or misconceptions the students in the case study are displaying, what the teacher did to inspire student learning, and what you learned from the case study that you'd like to incorporate in your classroom. So for whatever case study you're assigned, you'll answer those 3 questions in 3 paragraphs. And then for the rest of the case studies, you're going to make a comment on your classmates' posts that basically replies to what they said or what you learned from that case study. So rather than making a 3-paragraph analysis, you're just going to make a quick, like 2 or 3 sentence comment on your classmates' posts. So this is why it's important to do these case studies on time, is just so that everybody has a post to comment on for the other case studies that they were not assigned. Now, if it so happens that everybody who was assigned a certain case study didn't have time to write their post in time, you can just make a solo post with like a sentence or 2, sharing what you learned from that case study. And that will count as a comment if there are no posts available to comment on. But ideally, if you guys can, I'd like you guys to write your 3-paragraph analysis early on in the week so that by the end of the week, everyone can post their comments. And just for the sake of grading, because of the way that it shows up on my end, if you guys can put the case study letter at the beginning of your comments and the beginning of your posts, that will make it easier so that I know which one you're commenting on when I'm grading. So like, let's say you were assigned to do case study A, you would write case study A, and then you'd write your 3 paragraphs. And then when you reply to your classmate who did case study B, you would write case study B and then write your comment. Any questions about that? Okay. Oh, I did see a comment in the chat. Let me look at that. Okay, Carrie, it could be that maybe it's because you were added to the class late. So send me an email and I'll go in and add your name. I know I put in everybody's names over the weekend, and I know some people got into the class a little bit later than that. So just send me an email and I can do that. Or if you want to get started on it tonight, you can just decide which case study you're gonna do. Like, I don't know if you're in this section or not, but like basically the next blank space is where I'll put your name. So you can get started on that if you want. Amy, so those will be posted in the discussion board. So these case studies where all of the links are, you'll have a discussion board that you can post. So you can see some people have already done that. And you just do that by clicking on the reply button. Yeah, so Christina, you post the 3-paragraph analysis in the discussion board as its own post, and then for the comments, you reply to other people's posts. And that will submit the assignment. Yep. Okay. So, let me see if someone's seeing this. No, so you don't have to reply to everyone's discussion post, but you do have to reply to one discussion post for each case study. So like if you look at case study A, it's assigned to 4 different people. You only have to respond to one of those 4 people, but you do have to respond to A, B, C, D, E, and so on. Anita, will you send me an email? And I will add you to that. And by the way, guys, I teach two sections. So if you're not showing up on this one that I'm sharing on my screen, it could be that you're in the other section. So open up your case study assignments in your class, and check and see if your name is there. Okay, so that's the case study assignments. Also, so like when I grade them, you get 80 out of 100 points for your 3 paragraph analysis, and then you get 20 points for commenting on your classmates' posts. So I will grade it after the due date. But if you make some of your comments after the due date and it's after I've already graded it, I'd like to ask you guys to send me an email, because it doesn't automatically show up on my to-do list. If you have already posted a discussion post, but you didn't do all the comments. So like if you get 80 out of 100 points because you did your own post, but you didn't reply to the comments, just send me an email once you've made comments on everybody else's, and I'll go in and manually grade that. But it doesn't automatically show up on my end. I do need you to email me if you get partial credit and then you later finish the assignment. And I'll send out reminders about that, um, if needed. So that's the case study assignment. Let's look at the homework assignments next. So these are the ones that are worth 10% of your grade. And the main purpose of this is to help prepare you for the final. So on the homework assignments, you'll download the assignment. You can complete it digitally or on paper if you want. And you'll basically just go through and do whatever topics are on there. And again, the videos and readings assignment will give you the information you need to be able to complete the assignment. And then after you complete the assignment, you'll use the answer key to check your homework. So you're not actually going to send this to me. It's just graded on completion. But you can use my answer keys to check your work to make sure you understood the concepts, and correct your misconceptions. And if you have any questions, you can always send me an email. And then once you've done both of those things, you'll just submit a quiz certifying that you finished the assignment. So the homework is pretty straightforward. And again, you're welcome to submit it late if you need to. In fact, these would be the assignments I would recommend doing late, if you have an overwhelming week. Because ultimately, the homework doesn't have to be done until the end of this semester when we take the final exam. Because the homework is mainly designed to help you prepare for the final exam. Any questions about the homework or how that works? Awesome. Then the last one I want to go over is the conjecture projects. So the conjecture projects, the goal of this is to have you guys practice observing and noticing patterns and using algebraic notation to describe those patterns and then proving that those patterns will always work. So in these videos, which some of you may have already watched, I give examples of what proofs look like, and also how to write them. So there's two different types of proofs that will be useful in this class. The first one is an equivalence proof, and the second one is a proof by induction. So for the first, I think it's like the first 3 weeks, the equivalence proofs are the ones you'll be using the most. And then later on, you'll be using proofs by induction. So I want to quickly go over examples of what this looks like. So you kind of have an idea of what these projects will look like. So let me share my quick. I guess I have to stop. Maybe I have to stop sharing that one. There we go. Okay. So I want to start off with an equivalence proof. And I'm actually going to do one that's from your assignment for this week. So this week, the patterns that you guys will be noticing and observing are the relationship between evens and odds um, when you add and multiply even and odd numbers together. So let's say, for example, we were going to add two even numbers together. This is something sure you guys, some of you guys have even taught your students. But if you add two even numbers together, what type of number does it always equal? Go ahead and type it into the chat. Yep, exactly. Perfect. So when you do an even number plus an even number, the result is always even. So that would be our conjecture. And if you're teaching this to little kids, it will obviously take them a little bit longer to come up with that conjecture. Um, but it's definitely something that they're capable of doing. And for a child, the way that they might prove this conjecture is not going to be formal, and that's okay because that's appropriate for their age range. So, the way that a child might prove this conjecture is they might say something like, well, even numbers always come in pairs. Whether it's 2, 4, 6, 8, or whatever, even numbers always come in pairs. So, if I have pairs, like let's say I have the number 6, and then I add that to the number 4, which also comes in pairs, the result of combining those together is still going to have pairs in it. And so a child's proof for this will be very picture based, and it's not going to necessarily have a lot of formal algebraic notation in it. Um, so that would be an example of how a child might prove this. And what I want you guys to do in these conjecture assignments is to practice using algebraic notation to prove whatever conjecture it is you're trying to prove. So for you guys as adults, what I would like a proof to look like is you would say, okay, let's say that I have two even numbers. And the algebraic definition of an even number is that it's any number that can be expressed as 2 times an integer. So n is representing an integer, meaning like a number like 1, 2, 3, 4, 0, -1, -2, but no decimals and no fractions. So that's the definition of a even number algebraically. And that's how you would use notation to describe that concept of even numbers coming in pairs. And if I take two even numbers and add them together, so let's take another even number, and notice here that I'm using two different variables because the integers are different. Like, for example, if you're describing the even number 6, the integer that would go in this spot would be a 3 because 6 is 2 times 3. Versus if you're describing the number 4, the integer would be the number 2 because 4 is 2 times 2. Does that make sense why I would use two variables to represent that? Give me like a yes or a thumbs up or something in the chat. Yeah, so Melissa, this would actually just be like a generic any two even integers. So any even number that you could think of could be expressed as one of these two terms. Like if the even number was 104, what that would be 2 times 52. And that's what makes it an even number. It's the fact that you can have an integer or a whole number and multiply it by 2 to get your even number. In contrast, I'll write this in red so we don't mix it up. In contrast, an odd number is any number that can be written as 2 times an integer plus 1, because you have however many pairs that you do, and then you have one extra that isn't paired up with anything, and that's what makes it an odd number. So going back to this idea of adding even numbers, we have two even numbers that we've added together, and this expression can represent any two even numbers. It could be 6 plus 4, it could be 104 plus 28. Any two even numbers could be expressed in this form, depending on what integers are represented by n and m. And so to prove that an even number plus an even number always equals an even number, we need to show that this is equal to 2 times some integer. And the way that you would do that in this case is by factoring. So factoring is basically like the opposite of the distributive property, where since both of these have a 2 in common, you can factor the 2 out, and you're left with the terms n plus m inside of the parentheses. And the reason I say it's the opposite of distributing is because if you were to distribute the 2, then you would end up with this expression. So the algebraic proof for why an even plus an even equals an even would have this math sentence in it, because you take your 2 even numbers, which are in the form of 2 times an integer, and when you add them together, you can algebraically manipulate that expression so that the result is 2 times another integer, because one of the properties of integers is if you add 2 integers together, it equals an integer. So for your conjecture project, you guys will be proving a couple different conjectures like this. And basically what you need to do is create algebraic expressions that represent the idea or the pattern you're trying to describe, and then show why that equals whatever it is you're trying to show that it equals. Yes, Amy, thank you for asking. So in your proofs, the way that I think about a proof is basically as a math essay. So you will include mathematical notation like this, but I also want you to explain the reasoning as you go. So for example, with this even plus an even equals an even proof, you would say any even number can be expressed as 2 times an integer. So let's have the first integer, or sorry, the first even number be represented by the expression 2n. And you would like type all of that out. So what I just said in words, you would type that out. And then you'd say, this, let's have the second even number be represented by 2 times m, because it may be a different even number than the first one. And so you're explaining where those 2 pieces of your notation came from. And then you say, okay, if I add these 2 together by the distributive property, I can factor out a 2. And again, you're describing all of this in words. And so 2n plus 2m equals 2 times n plus m. And again, you'd explain all that in words. And then you'd say, because an integer plus an integer is an integer, n plus m is an integer, and that means that the result 2 times n plus m is an even number, because even numbers are expressed in the form as 2 times an integer. So Mrs. Franco, you do need to write it out. You don't have to type it. I know sometimes math can kind of be cumbersome to type it. So you can write it out by hand, as long as your handwriting is legible and I can read it. Let me actually think about that. If you can keep your recording under 5 minutes, I'm actually okay with you doing a recording. But it does need to be under 5 minutes, which I think might be hard for quite a few of these. But if you can keep it nice and short, I am okay with you recording it. I just decided that. Yeah. Just make sure the recordings are high quality and all of that. And it might take me a little bit longer to get you feedback on it, just because I'll kind of be in the rhythm of like marking up the PDFs versus watching a video, but that should work. Oh my goodness, yes. By all means, yes. Please record yourself if you had surgery. Yeah, thanks for asking for that. All right. Any questions about how to write those conjecture proofs? And again, I did make some recordings, or I mean, yeah, I made recordings, but also some examples. So these links right here, the example equivalence proof and example proof by induction, those 2 are examples of what a typed up proof would look like. So those can be really helpful. as you're figuring out how to write the proofs. I would recommend watching the videos first, because in these videos I explain the thought process, and then I typed up the proof so you could see what it looks like. Um, yes, yes, Christine. So this is what you'll see when you open up the conjecture project. And there's always a project guide that will kind of give you hints and some starting points. So like this one, you get the definition of an even and odd number, and then you make your conjectures for these things. So we did the first one together, just barely, the sum of two even numbers, but you'll also do things like the sum of two odd numbers, the sum of an even number and an odd number. And so you'll write up your proofs for those. Um, and I sometimes give you hints based on what I think might be helpful. And then uh, these ones are in all of the assignments so that you can reference back to them if you have questions on them. Or like questions about how to write a proof or what it should look like. Okay, so the proof that we just did was an equivalence proof. I was thinking it might be helpful to also do an example proof by induction, so that you can see how that works. Um, so let me share my iPad screen again. And then this will be the last thing, so we're almost done. But I do want to make sure we do this since I only get to see you guys like once this semester. Okay. Um, so let's say that the pattern that we were looking at was a visual pattern. So let's say that the first picture has a single dot. So this is picture one. Then on picture two, you have three dots like this. On picture three, you have five dots like this. On picture four, you have seven dots like this. So looking at this pattern, can you guys predict how many dots would be in the nth picture? So n is representing the picture number. And what type of algebraic expression could we use to represent the number of dots in the nth picture? Or if you want to, you can just share what you notice about the pattern. Okay, so Karen said that maybe 2n minus 1 represents the number of dots in the nth picture. Danielle noticed that it's n down and n across. Shri, yeah, this you could think of it as a function where the input is the number of the picture and the output is the number of the image. Okay, Jody's noticing that it increases by 2 every time. I hope I'm saying your name correctly. Makesha said that you take what I'm assuming what you're meaning by that is like this. Is that what you mean? Okay, awesome. Yeah, sometimes it's kind of hard to write it in the chat box. So this would be I think it's called sequence notation. But basically what this would be saying is that the number of dots in the nth term, so I used the notation Fn to represent that, equals the number of dots in the previous one plus 2. So that's kind of drawing on the same pattern that Jody noticed, where it's increasing by 2. And if we look at Kieran's number, where Kieran's saying that the nth or the number of dots in the nth one would be 2 times n minus 1. It looks like that would work because, like, for example, if n equals 3, where we're looking at the third picture, 2 times 3 um, would give us 6 minus 1 equals 5, which is the number of dots in the third picture. So this is what's called a recursive function, which means it builds on the previous one. So like it's saying you take the previous one and you add 2 to it. This one is called an explicit expression. And those ones tend to be a little bit more useful because if you wanted to figure out how many dots were in like the 100th picture, in this one, you could just do 2 times 100 minus 1, and that would tell you there's 199 dots in it. Versus if you were to use this one, um, it would basically be like you'd have to know the 99th one to be able to find the 100th one. But to do a proof by induction, you actually need to have both of them because the goal will be to prove that this is always true, regardless of how many times you iterate the pattern. And in order to do that, you have to know how the pattern builds on itself. Christina, so this is not what you would teach in first grade. This is so you guys have practice converting patterns that you notice into mathematical language. So in first grade, you're not going to be doing things where you're formally proving it, but I want you guys to go through the work of formally proving it so that you can practice turning patterns that you notice into mathematical notation. Because ultimately, that's what you want to help your students do as well. Like you want to help them make connections and realize things like 3 times 5 will equal 5 times 3. And this isn't just true for that math fact, it's true for any math fact. So the point of the conjecture projects is for you guys at an adult level to practice making conjectures and proving them. Um, so this one is less of a pedagogy focus, and this is more of a content focus. Melissa, there are many ways to prove it, but it does need to be a rigorous proof, meaning it's not just saying, and then the pattern continues. Like you need to explain why the pattern continues and why the expression describes the pattern that you're noticing. Whoever user is, you need to be willing to try. So you don't have to be good at it the first time. You're welcome to resubmit the assignments as many times as you need to get full credit. And I'm happy to help you with them. So if you get stuck on any of these conjectures and you're not sure how to prove them, I'm happy to help you with them. So you don't have to be good to start with, but you do need to be willing to try. Yes, exactly, Melissa. Yep. Mm-hmm. Okay, so going back to our proof here. So our goal, the conjecture that we're trying to prove, is that the number of dots in the nth picture is equal to this. And because this pattern is one that builds on itself, where you're adding 2 every time, the easiest way to prove this, it's not the only way, but one of the ways that I would recommend proving a pattern like this one is by induction. So the way that induction works is you prove what's called a base case, which basically just means you prove that your conjecture or your prediction works for the very first one. So what that would look like is you would say, according to the pictures, there is 1 dot in the first picture. And according to this formula, the first term is 2 times 1 minus 1, which equals 1. And because this gives us a result of 1, and the first picture has 1 dot, our base case is proven. So for the base case, you're basically just plugging in whichever, like your very first term, and making sure that your algebraic expression works for that first term. Is everybody good with the idea of a base case? And how that works? Okay. Got 1 person, now 2 people. If you have any questions about it, maybe let me know which questions you have. Okay, so this is the base case. And then the next thing that you do is you assume that your conjecture is correct for the term right before the nth term. So we are going to assume and base on fact that the term right before the nth term equals 2 times n minus 1, because I'm basically just plugging in n minus 1 for like my conjecture. And I'm assuming that that's true. And using that assumption, I want to prove that my conjecture is true for the nth term. So the way that I would do that is I would say, well, the nth term is the term right before it plus 2. Like that's what the pattern is. I'm consistently adding 2 dots every time. And so what that means is that the nth term would equal, assuming that the n minus 1th term follows the rule, it's going to equal that n minus 1th term. And then I'm going to add 2 to that because the next term is always 2 more than the previous term. And my goal is to use this and show that my conjecture is true for the nth term. So in this case, the way you would do that is you would distribute the 2, which would tell you that f of n equals 2 times n minus 2. And then you'd have the minus 1 and plus 2. And all of these terms can be simplified and combined. And if you do negative 2 plus negative 1 plus 2, that ends up giving you f of n equals 2n minus 1, which proves the conjecture. So the idea of induction is basically like you prove that it's true for one thing, and then you prove that assuming that the term right before whatever term you're looking for follows the rule you're trying to prove, that implies that the next term is. And the reason why this creates a rigorous mathematical proof is because if you prove that it's true for the first term, and then you prove that the first term implies the second term, and the second term implies the third, and the third implies the fourth, and so on, it's going to prove it for all of the infinite number of terms. In contrast, if you were to prove this like by hand, it would actually be impossible because if you just kept on plugging in numbers like we did here, like plug in for the second term and the third term, you literally have to plug it in for every single possible term out to infinity, which is impossible to do because infinity is infinite. So that's the idea of induction is you do this inductive step where you assume that the term right before it follows the rule, and you use that assumption to prove that the next term follows the rule that you're trying to prove. Melissa, typically, yes, you can technically assume it for the nth term and then prove it for the n plus 1 term, because it's still the same idea. So if notationally it's easier for you to do that, you can do that. But usually it tends to be easier if you assume the n minus 1 term and use that to prove it for the nth term. Yeah, good question. And if you guys need any help on this, on these inductive ones, I'm absolutely willing to help with that. And if you want to, we can even schedule kind of like maybe like a meeting where everyone can meet and we can discuss it as a group. Because I know that proving stuff can be a new concept, especially if you didn't do it during your undergraduate time. Um, oh, yeah, I do want my iPad to leave. So I'm happy to help you guys with these. And again, you're welcome to resubmit the assignments as many times as you need to. But the goal of those conjecture projects is to help you guys practice taking patterns and learning how to use mathematical language to describe and prove those patterns. And most likely you're not going to do something that complicated with your students, but you will be asking them to make conjectures and you will be asking them to prove those conjectures, even though their proofs will most likely be more picture-based and less rigorous than your proofs will be in this class. It's still important that you understand how a rigorous proof works, so that you can help draw your students' thinking out and help them understand why the pattern always continues instead of just saying, oh, well, it works for the ones that I noticed, and so I think it works for everything. because sometimes that's not always the case. So that's everything that I wanted to cover with you guys. If you have any questions, feel free to stick around. Otherwise, I'm excited to see the assignments as you start submitting them. And I'll send out emails and stuff with reminders of um, important things. And I hope that you guys enjoy this class. And I'm going to end the recording here just for the people watching it.